doing education and leadership department. I'm doing research in prosthetics, and today I'm happy to introduce to you a new redesigned volume adjustable socket for below-knee amputees. An amputation is the third most traumatic event that can happen to an individual after losing a spouse or a child. Amputations in the US are huge. Just in 2010, there was an estimation of 1.8 million amputees. From those, 86,000 amputations were due to diabetes. Also, 185,000 amputations are being performed each year, and 1 person out of 200 people has had at least an amputation. Amputations are categorized in two parts, upper limb and lower limb. In this research, we are focusing in lower limbs, more specifically below the knee. Why? Because from the 100% of the amputations, it's been reported that 86% of amputations are being performed lower limb. So that's why we are focusing in lower limbs. Our feet are specifically designed to transfer our weight and forces in the most comfortable way. Following an amputation, a prosthesis must mirror this behavior because the residual limb shrinks and swells a lot after the surgery. Unfortunately, current solutions are carbon fiber and plastic shells that do not effectively adapt to these changes, causing blisters, calluses, ulcers, and other skin problems that can lead the patient to hospitalization or to spend a lot of money in prosthetic replacements. In 2014, Dr. Megan Kendall introduced the aperture socket. This is a volume adjustable prosthesis that is able to adapt its volume plus and minus 15% in a radial change, local and uniform. It also has other features such as a manual adjustment mechanism with simple tools. It also keeps the same maintenance procedure and keeps the same manufacturing materials. Its weight only increased less than 180 grams, which for patients were not able, they weren't able to notice this weight. So for them, it was pretty good. After she tested her prosthesis and in mechanical machines and with patients, she noticed that still the prosthesis needed some improvements. So she planned these design improvements for the future, which are create a faster adjustment mechanism for at-home adjustments, to make it more simple, to reduce the relative movements of the different plates that overlap each other, to expand to other suspension systems, and to create a manufacturability process easier. So when I started working with her, we designed and we defined our design methodology in 4 different stages. First, we define our problem, we design, we want to test and deploy. In the definition process, we gathered some requirements. We analyzed these requirements, and then we started with designing conceptualizing our designs and prototyping all of our designs using additive manufacturing, also called 3D printing, and we use a verification method called demonstration, which is a verification method from the systems engineering department. Future stages include the verification test in mechanical machines, and also validation test using human interface techniques, also from the systems engineering department, which is testing our socket in amputees with lower limb applications. And after that, after I finish my thesis and I present, future stages also include deploy our socket either in the market or for nonprofit organizations. So this is a aperture socket designed by Dr. Megan Kendall. It consists of 4 different plates that overlap each other, and they are kept in place by 2 Velcro straps. Also, it has a adjustment mechanism at the end, more like a camera aperture, that rotates and expands and collapses these 4 different plates, and allowing a different volume change as the user needs. So in order to address these design improvements, we did a vast literature review in which we compare other systems and we compare other researches such as Dr. Sanders from Washington and other sockets in the market. And then we went out of the building. We participated in the regional EXPO program from the National Science Foundation. We interviewed a total of 23 stakeholders. From those, 18 were certified prosthetists, also called clinicians. I want to address that word better. They said the fit is still a major problem and that the patients, they don't usually follow instructions. And they said that the technology is pretty good in prosthetics, but they want us to keep it simple because it's hard for them to manufacture all these prostheses. Then we also interview amputees, and we interviewed a total of five lower limb amputees. They said that the constant change in residual limbs is still a pain for them, and that they need to change their prosthesis every 1.5 years. So it's super expensive for them to keep changing prosthesis every year and a half. So they just kept their prosthesis in the closet because it's not longer fitting well and it's causing a lot of pain for them. So we came out with this preliminary design in which it also consists of 4 different walls, or socket walls. They also overlap each other and they are kept in place with 2 Velcro straps. These straps they have a different locking mechanism. It consists of a bolt with a small lever that allows an easier adjustment for users. Also, it has 2 different discs. One is the rotary disc that goes in the top and a transfer disc. This transfer disc has 4 different transfer guide screws, and what it does, it's sort of rotating the transfer disc and collapses and expands the guide screws that are in the transfer disc. After that, we checkmark our first 2 planned design improvements, which is creating a faster adjustment mechanism and to keep it simple. However, we found out that using Velcro straps is not feasible because most of the amputees are diabetic people and they don't have, they are not strong enough to apply the force necessary in order to collapse these 4 different plates and to come up with a more comfortable adjustment. So we also participated in the national program of the National EXPO program from the National Science Foundation, and we interviewed a total of 111 stakeholders, including practitioners, amputees, and other stakeholders from the area. And from here, they gave us a lot of good feedback in which a good adjustment mechanism can be. They said that we needed to keep protecting the bony parts, which is the tibia and the fibula head, that we cannot mess with that by collapsing them because that's going to hurt a lot for the patient. So we came up with our detailed design that I'm presenting now. It consists of a flexible socket and 4 different struts. These struts are also made of carbon fiber, and these struts collapse and expand each other as the rotary disc functions. One of the strut that is in the front is fixed, protecting the tibia part, and the other strut also protects the fibula head. So the other struts compensate the volume loss in the muscles by collapsing and expanding as the user needs. So instead of the Velcro straps, we now are going to use power straps, which are straps powered by rochettes, and this is going to provide a more comfortable adjustment for patients, so they are not going to apply a lot of force as needed with the Velcro straps. Also, we're using 3 different guide screws for the struts that are going to compensate the volume loss for the muscles. With this, we checkmark all applying design improvements, which is come up with a faster adjustment mechanism for palm adjustments, keep it simple, to reduce relative movements of plates, expand to other suspension systems other than the pin lock that is a conventional suspension system that amputees are using. It consists of a liner and it has a pin at the end and it locks with the prosthesis. Now we're using suction system that includes sort of a vacuum whenever the patient wears the prosthesis, takes out all the air, creating a vacuum for a more comfortable fit and for a better latch with the prosthesis. For future work, we're going to test our socket using a modified ISO 10328 standard setup This is a compression test by mechanical machines, and we're going to modify the version by designing some jigs that one of our colleagues in the ELE department is working on right now. And once we get the IRB approval, we want to test our socket with humans. So as a result, now we are providing a more comfortable prosthesis for lower limb amputees, which is the main problem that all the prosthetists and amputees are complaining about. They say they cannot compensate volume, they spend a lot of money over time, and they don't have a very comfortable fit during the day. So whenever they have volume loss during the day, they need to compensate this volume loss with socks, which includes the moisture and increases a lot of temperature that is going to make them feel very uncomfortable. After that, hopefully when I graduate and Dr. Kendall is going to take care of the socket, they're going to deploy our design with Limbs International, a non-profit organization that is based in UTEP. And they are providing this neat, very cool, low-cost prosthetics for the developing country. So there goes my boss, Dr. Kendall. Thank you. Now we have the vector straps just for presentation, but in the future we're going to get the power straps, and this is the different mechanism that I was talking about.
Okay, let's go ahead and open the floor for about 10 minutes for questions.